Welcome to our third video about the normal distribution. In this video we will start to introduce ideas of using the normal distribution to solve problems. Have a look at this image. What parameter has changed here? What is the area under each curve? Well, it's pretty obvious to see that the mean has changed. The area under each curve must remain as 1. In this one, the parameter that has changed is the variance, or the standard deviation squared. The area still has to be 1 underneath each curve, but if you look at it closely, two things have happened to the curve. We've got a vertical stretch and a horizontal stretch. To preserve the area as 1, if there is a vertical stretch, then there must be a horizontal stretch as well to compensate for that vertical stretch. And what we're studying in this video is the standard normal distribution, which has mean 0 and standard deviation 1. And it's a really handy thing for us when we don't know the mean and standard deviation of a normal distribution. We can still find out things by relating our distribution to the standard normal distribution. Now, in the textbook, they use small case phi for the PDF and capital phi for the CDF, which you'll get used to. So, when Z is distributed normally with mean 0, standard deviation 1, find the value of capital phi of 1. So that's CDF. That means the probability that Z is less than or equal to 1. And phi inverse is the inverse normal. So in other words, what is the value of Z such that the probability Z is less than that value is 0.8. So try that on your calculator for a moment, pause the video. There's the answers. Now, the answers look pretty similar, so it's a good idea to draw a sketch just to convince yourself that everything makes sense. Okay, now don't laugh at my terrible use of my new graphics tablet. Yeah, stop laughing. Okay, so for A, the mean is 0 and the Z value is 1. So the probability Z is less than or equal to 1 is 0.841345. That seems to make sense. It's got to be quite a lot more than 0.5 because it's gone over the halfway line given by the mean. On the other hand, phi inverse of 0.8 means what is the Z value here that we would go to accumulate an area of 0.8, and the answer is 0.841621. And that kind of makes sense because that's less than 1. Remember, we had to go as far as 1 to accumulate this area, and this area is bigger than this one, so it makes sense that we don't need to go as far to accumulate a smaller area than this. As always, a simple sketch, even a terrible one like this, helps you orientate yourself, just like the unit circle does for trigonometry. Now, if you have to solve a problem where you do not know the mean or the variance, you have to use the standardized normal variable. And this is the formula for the standardized normal variable. It's in the formula book. Analyzing this and proving everything is a little bit beyond what we're doing in the core of higher level maths. The basic idea is truths and probabilities in this distribution are directly related to truths and probabilities in this distribution. And the beauty of it is, if we don't know mu and sigma squared, we can still find things out by translating over into this distribution. As we will see here. Now, don't be scared by this. This is showing that if you have an event here where x is distributed normally mu sigma squared, and you're having to find something out about this event, in fact, making a substitution like we do in integration, z equals x minus mu over sigma, enables us to rewrite this integral and rewrite this event. Because this event, if we apply the same formula to all three things, it's actually the same probability. Because if this event happens, this must happen, and vice versa. X minus mu over sigma is what we call z, and z has the standard normal distribution. Now, if you look closely here at the consequences of the integration substitution, if you look closely, you will see sigma z affects a horizontal stretch of 1 over sigma, and sigma outside the brackets affects a vertical stretch of sigma. So those two things cancel out to preserve the total area as 1, because you're stretching 1 over sigma in one direction and sigma in the other. And when you carry out the integral, just like we usually do by substitution, and it's just gone off the page there. Let's see if I can bring that back. Yeah. Just at the bottom of the page there. You can see that this integral simplifies to f of b minus f of a equals I. I is the original event. So basically what I'm trying to show you here is that this probability where x is distributed with these parameters is exactly the same as this probability where we transfer over to this distribution. In other words, you can always find out something about this distribution by transferring over to a different distribution. Now, don't worry if that was a bit difficult. It's a little bit beyond what we usually do at this stage. To demonstrate that, you might want to try this problem with your calculator and look at the answer in the book, example 35. And you'll see what the previous page was all about. So I'll leave you to do that for a second. Now, as an introduction to the next video, this is where the standardized normal variable gets really useful. So here we're given x is distributed normally mu sigma squared, and we have to find those values. We don't know either of them. We're just given these probabilities. So if I just take the first one, yeah. Okay, so the probability x is less than or equal to 2 is 0.546. Using z, I can transform that to z less than or equal to 2 minus mu over sigma. And you might think, well, so what? What's the progress there? Well, the fact is, in the first statement here that I wrote, we don't know anything about the distribution of x. But in the second statement, we know everything about the distribution of z. It's distributed with mean 0, standard deviation 1, and that enables us to progress, as you will see in the next video.